Okay, morning everybody. Let's get started. Undergraduates, you are moving on to assignment 5, where you are going to be pausing and pivoting. What you're going to be doing in the first part of assignment 5 is doing some refactoring. So you've written a fair bit of code up till now, and assignments 6 through 10, you're going to write a lot more code, and then yet more code once you start working on your final project. So we're going to pause this week and clean everything up, refactor, and modularize your code so that it is easier to add code as you go. Most of you have already had the experience that if you start to work on a piece of code, the longer and longer it gets, the harder and harder it becomes to add new functionality to it, right? So a little bit of housekeeping this week. The main thing you're going to be doing during this refactoring process is adding some classes and class instances to your code, making it more object-oriented. For those of you that are a little bit rusty with the concept of object-oriented programming, or you haven't done that in Python before, I would suggest before you tackle assignment 5, go find an online tutorial about doing object-oriented programming in Python, work your way through that tutorial, then tackle the objectification of your assignment code base. Okay. Once you have done that, in the second part of assignment 5, now that your code's all cleaned up, you're going to be implementing the simplest of all the search algorithms. I mentioned last week, I think, the hill climber's the simplest. It's not the simplest. The real simplest is choose a bunch of random solutions for however much computational time you have, and at the end of that time, give us back the best thing you found, right? Clearly not a very intelligent way to search a vast search space, but it certainly is simple, right? So you're going to clean up your code, exercise your cleaned code by wrapping random search around your PyroSim simulation, right? So you're going to be basically adding a bunch of more complex shells around your base simulator now. And all of these search methods are going to have the same thing in common, which is that they are going to start and stop a whole bunch of simulations with slightly modified robots in them. Okay. Graduate students, you are moving on to assignments 9 and then assignment 10, the final assignment. Graduate students, you will find that when you finish assignment 10, you are not at the end, you're at the end of the beginning. So in assignment 10, you're going to be replacing the fitness function, which up until assignment 9 has been selecting for forward locomotion. You're going to be selecting instead for phototaxis. You're going to evaluate your robot 4 times, and in those 4 instances, the first instance, you're going to place a light source in front of the robot, then a light source behind the robot, then a light source to the right, and a light source to the left. And as you can imagine, higher fitness is awarded to robots that can turn and walk towards the light source regardless of where it's placed in its environment. This is a notoriously difficult thing to do. We are not looking for you to submit a video at the end of assignment 10 showing a robot that can move towards all 4 light source placements, because that is next to impossible without use of the supercomputer here at UVM. Most of you probably don't have access to the supercomputer, so you probably will not have enough computational effort for your evolutionary algorithm to find a phototacting neural network for your robot. What we are looking for is that your evolutionary algorithm is on the way towards phototaxis. So submitting a video in which the robot walks forward in all 4 when you play back an evolved controller and you shoot a video of it, if that evolved controller causes the robot to move forward in exactly the same way in all 4 environments, that's not what we're looking for. We should see that the robot is quote unquote paying attention to the light source. Maybe it walks towards the light source in 2 out of the 4 cases, maybe 3. That's what we're looking for. Okay. As I mentioned, this is a notoriously difficult task to solve. It requires a lot of computational effort with the relatively simple robot and simple neural network and simple evolutionary algorithm that you have in there. Graduate students, what you might want to do at the beginning of next week instead of immediately tackling your final project, is to start to complexify some of the components of your code base. Make a more sophisticated fitness function, empower your evolutionary algorithm in some way, maybe add a hidden layer to the neural network controller inside your robot. By the time you get to the end of 10, you'll have an idea of sort of the things you can change and try and empower to improve your robot's ability to perform phototaxis. Sound good? Any questions about any of the 10 assignments at this point? No? All good? Okay, so back to lecture. We are making our way through the history of evolutionary robotics, and as promised, we're going to look at two branches. The first branch is this idea of minimal cognition. Let's make simple agents, and as we saw last week, they're all going to be running a CTRNN, which is not a minimal neural network, but a CTRNN has an important property that we're going to see in action today, which is its ability to enable the robot to do different things over different time scales, right? Walking, which is a fast time scale task, while at the same time having a conversation with your friend, a slightly slower, a task that unfolds over a slower time scale. We're going to see some examples of that in our minimally cognitive agents today. We may start in on another branch of this, or another aspect of minimal cognition, active categorical perception. And then either on Thursday or at the beginning of next week, we're going to look at the second branch in the history of evolutionary robotics, which is motion. And as promised, there is a fundamental relationship between figuring out how to get yourself from point A to point B, so self-motion, and intelligence. And we'll come back to that when we get there. Okay, so in my personal opinion, this is one of the more fun lectures in the course because we're going to look at this paper, which is in the bottom right. Undergraduates, you might want to just read the abstract, the very beginning of the paper and the conclusions. Graduate students, I would suggest you put some effort into reading and understanding this paper in a fair bit of detail. It's a landmark paper in the field. What they did in this paper was to look at 4 different tasks which require different building blocks of intelligence, right? So as promised, we're going to look at something that looks like a physical Turing test. We're going to try and evolve machines that are maybe not intelligent in and of themselves, but that embody different aspects of intelligence. We are not going to see any agents that embody all 4 of these tasks. We're going to look at specialists that only are able to do one of the 4. Getting agents to do multiple things, like walking towards 4 differently placed light sources, is difficult. It's still an open problem in the field. Okay, so let's start with the first of the 4 building blocks of intelligence, and this is perceiving affordances. So what is an affordance? For those of you that have taken my HCI course, you may remember our discussion about affordances from there. An affordance is something that an object advertises, or from the lingo of psychology, it's something that an object affords. I have 5 objects to the left. What do they all have in common? They allow us to sit, right? So all 5 of these objects, when shown together, most of you, hopefully, can immediately perceive the common affordance, the advertisement. Each of these objects could emit multiple advertisements or multiple affordances, but there is clearly one that they all share in common, which is that they afford the ability for a human adult to sit in them, right? So one of the things that held up computer vision for decades was trying to get machines to recognize objects and images based on the geometry of the image itself. And what psychology, which formulated this idea of affordances, taught us is that when we perceive our world, we are not just paying attention to the geometry of the objects, we are paying attention to 2 additional features related to those objects. Something to do with the observer, who is observing the object, and what are the possible interactions between that observer and the object, right? What possible actions are possible? As we'll see as we continue on in this course, a lot of the building blocks of intelligence, as we've already said, have a lot to do with action and the body, right? If I were to ask you, before I put up this slide, if I were to ask you to describe a chair, most of you would probably give me a geometrical description, right? It has a flat seat and 3 or 4 legs and a straight back. You may or may not mention the human anatomy and the act of sitting itself. You'd tell me the geometry, and most people would leave out the observer or the person that's trying to do the sitting and the action. Thinking about thinking is misleading. When you think about how you recognize objects in the world, in your conscious mind, you're usually conscious of the geometric properties of that object, and you're not really conscious of your involvement in the recognition of that object. You can play the affordance game today as you walk around campus. You will probably push and pull a lot of doors today. As you approach a door, pay attention to the geometry of the door itself. How well is the door doing at projecting the affordance, one of the 2 affordances, which is whether the door is pushable or pullable, right? Another way to think about affordances is, what are the adverbs that come to mind when you observe the object? Actually, this door up at the front is a perfect example, right? A door bar is pretty good at projecting just one of the 2 possible affordances of a door. Which one is it? Push, right? When you look at that bar and you visualize your hand reaching out for that bar, it doesn't make a lot of sense to think about pulling on the bar. It somehow feels awkward or difficult or not what you're quote unquote supposed to be doing, right? It feels much more comfortable to imagine your interaction with that object as pushing. There are a lot of other doors on campus where it is not that clear, right? So as you perceive the various doors in your environment today or any object, think about the affordances that it's projecting. Try and ignore the geometry, which is usually what rises to mind, and focus on your potential interactions with that object. Okay, so we do this, and we're not always conscious of it. How do we get a machine to do this? If we had a human-sized robot in the room, we would prefer that when it looks and approaches the door, that it tries to push without pulling or twisting or tapping on it. It should be able to figure out or be able to think about its potential interaction with the object and get it right on the first time. Not an easy thing to do. Okay, this is just another example of affordances. Obviously, I'm leaving one of the objects in place here and showing you a different set of objects. This is just a reminder that any individual object is projecting multiple affordances at the same time. What is the common affordance of these 4 objects? Fuel, right, or an energy source. Hopefully, when you see this picture, the tree stump affords energy use, and in this case, it affords sitting. So the kind of affordance that rises to mind is, again, not even just limited to the object itself and the observer and the potential actions. It has to do with background context. What else is going on? Okay, so let's look at the first of our 4 minimally cognitive agents from this paper. And what they're going to do in all 4 cases is use an evolutionary algorithm to evolve a robot to exhibit that behavior, which in our case, for the moment, is perceiving affordances. We are not going to talk today about the details of the evolutionary algorithm and the neural network. For our purposes, just remember that there is an evolutionary algorithm in the background. It is evolving various aspects of the CTRNN, which are what? What are the things in the CTRNN that are being evolved by the evolutionary algorithm? Sorry? Tau, right? So the time constants. What else? Tau.
Weights, gain, bias.
Weights, gain, and bias, right? So these 4 sets. The weights are a matrix because we have ij, and all the others are vectors, right? Again, we won't worry for the moment about the number of neurons, the number of ordinary differential equations in here. We've got a CTRNN under the hood, and we're going to train this minimally cognitive agent here to move back and forth along the bottom of the screen, Space Invaders style, and pairs of objects are going to fall from the top of the screen. As you can see in this little cartoon here, this robot has 4 motors. It's so simple that it's not clear whether these are wheels or rockets or doesn't matter for our purposes. It can just push itself left and right. And the robot can look above itself, and it has 7 proximity sensors, which are these 7 beams emanating from the robot. And at every time instant in the simulation, it's getting back the lengths of these 7 beams, which are being fed into the CTRNN, which influence the 2 forces that push the robot back and forth along the bottom of the screen. Right? So the agent's body is pretty simple. Its environment is pretty simple. Still kind of a physical simulation, but a pretty minimal one. We're in 2 dimensions here. What is the affordance? Well, the affordance is these pair of blocks are falling, and the robot has to figure out whether the aperture or the gap between the objects is passable. Adverb, right? So can the robot, if it gets directly underneath the object pair, will the pair of objects fall to the left and the right of the object of the robot, and it will safely thread the needle, right? Get through the gap. Okay. Again, pretty simple. Let's have a look at the fitness function, which for these authors, instead of fitness, they use performance. So the P is for performance. They're going to evaluate each CTRNN num trials times. So they're going to do a number of trials with the same CTRNN, and they're going to take the average performance of the robot during those number of trials. So P sub I is going to be a single number which represents the performance of the robot of the CTRNN during the ith trial. Tell me about P sub I. We've got 2 pieces here. Let's have a look at the first one. So the first computation is performed if the opening between the pair of objects is too narrow for the robot to pass through. What is this fitness function or this performance function selecting the robot to do when the gap is too narrow?
It depends on how great DI can get, but it seems like it's trying to avoid the walls, but also avoid the blocks.
Yes, sorry, there's no walls. Imagine, I know there's a ring around this. Imagine there's no lines here. So it's an infinite arena. It can go to the left and right as far as it wants. What should it do when a pair of objects starts falling from above and the width of the gap is narrower than the width of the robot? Pick one of the blocks, and
go under it.
What happens if it goes under one of the blocks when the gap is too narrow and the blocks are falling? So the pair of blocks fall together at the same velocity, and they have this gap in between. If the robot, quote unquote, picks one of these objects and goes towards it, what's going to happen? Sorry? It's going to collide, right? This is not what we want the robot to do. It's got to be, the adverb here is passable. It has to pass through the gap.
It wants to, well, if it's too narrow, then it should try and avoid the blocks falling down.
It should try and avoid the blocks, right? So how do we do that? We tell the robot, get out of there, run away, right? So I'm sorry for those in the back, it may be hard to read here, but you'll notice that P sub I is a function of D sub I, and D sub I is the final horizontal separation between the robot and the center of the pair of objects when the object pair gets to the ground, right? So maximize D sub I, run away. If it runs away and does not collide with the, oh, I'm sorry, this is a misprint here. This should not be wall. This should be if it collides with either of these 2 objects. Author's fault. Okay, this should be collides with one or both of the objects. If it does not collide, it gets a score of 100, which is good. We're trying to maximize P sub I here. If it does collide with one of the objects, the performance is 2 times the absolute value of D sub I. For our purposes, just focus on the fact that P sub I is proportional to D sub I here. The bigger D sub I, the better. So you can imagine early on in evolution when the robot doesn't know what to do, it's moving around randomly underneath the object pair, and from time to time it's getting hit. And every time it gets hit, we compute d sub I, and robots that get hit but are slightly further away from the center of the object pair when it gets to the ground have a competitive advantage in the population of evolving CTRNNs. Can everybody see that? Okay. Those that don't get hit, that's great. So remember, there are multiple pairs that are being dropped on the same CTRNN, one after the other. Some of those pairs have a gap that is unpassable. It's too narrow for the robot to get between. And some of the times the aperture is wide enough. It is passable for the robot to get between. So in those cases, in those trials where the aperture is wide enough, they compute p sub I like this. Tell me about this component of the fitness function or the performance function. What is it selecting for and what is it selecting against?
If it's between the blocks, it obviously has the highest fitness, and it's choosing to rank the ones that got hit higher because it's then getting closer to succeeding than the ones that are beyond the block.
Absolutely, right? So the best thing you can do, obviously, the robot can do is be between the blocks. If the passable aperture gets to the bottom of the screen and the robot doesn't get hit and it's beyond the blocks, that's the worst thing it can do. It's run away in the case where it should not be running away. And if it gets hit in this case, again, for our purposes, let's just focus on the fact that p sub I is proportional to the negative of d sub I, right? The less d sub I is for a robot that gets hit by an object pair with a passable aperture, the better, right? Move towards the center of the objects. So even if you're getting hit, get closer and closer to the center until you're not hit at all and you manage to let the two objects fall to either side of you. Okay. If we evolve these CTRNNs using this performance function, and at the end I show you a video of the best evolved CTRNN, what do you expect to see? Assuming the evolutionary algorithm did its job.
If there's a passable gap, it will go through this, and if there isn't, it will move either way.
Absolutely, right? So if I put you in front of a whole bunch of doors, some of them that have a bar and some of them that have something that looks like you pull on it, I want to see that you always push on the bars and always pull on the thing that I want you to pull on, right? Can the robot not only evolve the ability to perform this task, but if it does, is it able to recognize the affordance? Is it able to move underneath the object pair and scan them to compute whether this gap is passable or not? We don't know how the evolved CTRNN does that, but we know whether it's doing it correctly by observing the behavior, right? This is a Turing test. We don't know what's going on inside the head of the agent. Very difficult to dissect an evolved CTRNN, as you can probably imagine, but we can tell whether it's doing it based on behavior. Okay, so let's look at that behavior. In this paper, we're going to look at a whole bunch of different kinds of figures that are meant to try and represent the behavior of the best evolved CTRNN. So down here, what you're looking at is the aggregate behavior of the robot when equipped with that CTRNN under a whole bunch of different circumstances. So the horizontal axis represents these different circumstances. We're going to drop a whole bunch of object pairs, and the ones that are to the left have an aperture that is too narrow for the robot to get between, and the right-hand half of the figure represents aperture widths that are wider than the robot's width. And the vertical axis is how far away horizontally was the robot from the center of the object pair when the pair got to the ground. What did this evolved CTRNN force the robot to do? Is this robot optimal? Does it do exactly the right thing all the time? Almost, right? As usual, evolution is a satisficer, not an optimizer. It's pretty good, but not perfect. Why pretty good? What's happening most of the time?
It is either avoiding the blocks or passing.
Exactly. If you look at the left side of the plot, the robot is far from the object pair when it gets to the ground, which is the right thing to do because it couldn't have threaded the gap. And the right-hand side of the figure, the horizontal distance is usually 0 or very close to 0. Most of the time, it threads the gap when the gap is passable. The robot knows, this evolved CTRNN knows the difference. What happens when the gap is almost the width of the robot? What happens towards the horizontal center of this figure? What's going on in this case?
Robot is far away from still far away from the blocks or the wall. It doesn't pass through.
It doesn't pass through, right? This is yet another version of the coward. If it's not sure, and even in cases where the aperture is a little bit wider than the robot, it still runs away, right? This robot or this CTRNN errs on the side of caution, which you could argue is not optimal, right? It should be a risk taker. If it's wide enough, it should always go for it. But if you look at the history of life on Earth, it also makes sense from a Darwinian point of view, usually to err on the side of caution. There's a great sub-literature on the evolution of religion and superstition, which has to do with the idea of agency. Imagine you're a small furry creature running down the path in the forest, and you see up ahead a leaf shake, just as you're starting to approach that part of the path. You imagine there's two possibilities for the shaking of the leaf. It's either the wind or it's a predator who's waiting for you. If you're not sure, which of those two hypotheses should you act on? It's a predator. Better to think that someone or something is behind the scenes, even if that may not be the case. Now, whether that really explains the evolution of certain aspects of superstition and religion, who knows? But it's interesting to see yet again that artificial evolution rediscovers something that biological evolution has evolved time and time again, which are cowards, right? Or agents that tend to err on the side of caution. It's a pretty good strategy. Not an optimal strategy, but a pretty good strategy in general. Okay, let's have a look at the two figures in the top left. These figures take a little bit to wrap your mind around, so we'll take our time here. Obviously, we have two panels here. The panel to the left corresponds to object pairs that were too narrow for the robot to thread between. And the panel in the right corresponds to dropped pairs where the gap is wide enough for the robot to get between. And again, both of these pairs were drawn, both of these figure pairs were drawn for one evolved CTRNN, the one we just talked about. Okay, so what they did in the left-hand one here is they dropped object pairs at different horizontal positions at the top of the screen. The first time they dropped it, the object pair was 40 units to the left of the robot, and this object pair was dropped 40 units to the right of the robot at the bottom of the screen. Yeah. Then the objects start falling. So the vertical axis represents the vertical height of the pair of objects. And as you can see at the beginning up here, the distance, the horizontal distance between the robot and the object pair is unchanging. That's what these vertical parts of the lines represent. The object pairs always drop perfectly vertically, which means that at this point in time, for the first 20 units of drop of the objects, the robot is staying still at the bottom of the screen. At this point in time, at least for this evolved CTRNN, the robot starts moving, which is represented by the diagonal lines, right? The objects are falling, and the horizontal position between the robot and the object pair is changing. Yeah? So these these black lines are not the trajectory of the object pair. It's drawing the horizontal distance between the object pair and the robot. Can everybody see that now? Okay. Tell me about this evolved CTRNN when the gap was unpassable. What does the CTRNN cause the robot to do? We're getting more of an insight into how the robot behaves now, not just how well it does. What does it do?
It usually moves towards the center of the pair, and then once the vertical position around 50, kind of scoots out of the way real quick.
Exactly. So you'll notice if we look right here at the center, the fact that all of the lines pass the center of the figure means the robot is passing underneath the center of the object pair. And in some cases, it's actually going back and forth before either it runs away to the far left or it runs away to the far right. Why are all these lines passing underneath? Why is the robot passing underneath the center of the object pair?
So you can see if we can fit in between the blocks.
Absolutely, right? So remember, we need to see through the eyes of the robot. In this case, it only has limited sensing, so it perhaps needs to get towards the center to see what's going on. Not only does it see, but it is actively, in some cases, sweeping underneath, right? Perhaps it is actively perceiving, and we'll talk about active perception in the next lecture, which is the idea that we don't sit passively and observe the world, although it may feel like you're doing that right now. But even now, you are actively perceiving. Your eyes are jumping from the screen to my face, to a point on the wall, back to the screen. You are actively perceiving your world all the time. Okay. Tell me about the case when the object pair, the gap is passable. What does the same evolved CTRNN do in this case?
When you feel like it's passable, it's always stay in the center.
It stays in the center, right? In all of these cases, the robot eventually gets right underneath the object, and then the fact that all these lines are perfectly vertical means the robot stops moving and waits for the pair of objects to fall on either side. When does this robot make a decision? When does it decide whether to run away or go for it? Yep.
It seems like in between the, like, say, like at the center when like around 60.
Around 60. Why around 60? How did you figure that out? Not why 60 for the robot, but how did you know that something's happening at 60? Why is 60 important?
Like in 60 is like always come straight.
They all come straight, and if you look at both figures above 60, the robot's behavior seems to be exactly the same, regardless of whether the gap is passable or not. It's only after 60, meaning the object pair is now less than 60 units above the robot, that it starts to do something different. So obviously, the robot must be making a decision at 60, right?
What were the sensors?
The sensors are these 7 rays.
Okay, so there's just 7 rays.
That's it. The robot, at every time step, the input to the CTRNNs from the outside world are 7 numbers, which are the lengths of these beams. Yep.
Is it just because it's 60 because it takes a time to like to the process the input?
Could be, right? It could be that only at 60 do the pair of objects touch the tips of the beams. It turns out that that is not the case. The robot is able to see the objects before that.
Is it just the fact that it's going back and forth and be ready to make that decision at 60?
Maybe.
Is it maybe that at 60, the distance between two of those rays is the same as like the width of the object itself?
Maybe evolution has come up with an easy hack. It's able to find some constancy in its world, right? That regardless of the falling of the object, if it's able to get in the right place at the right time, it triggers some threshold. A value above this, run away. A value below this, stay here or move in this direction. Maybe. There's hundreds of hypotheses you could come up with. Who knows, right? Whatever it is, it's probably not that simple. It is probably not the robot saying, okay, The objects are now 60 units above me. I'm here, they're there. What's the gap? What's the width of the gap? Run away, stay here. It looks like it's making a decision at a particular place and a particular point in time, but thinking about this agent's thinking is misleading. Who knows? You remember our discussion towards the beginning of the course of the very controversial Libet study about free will? I decide to move my finger at this time. I know I did. I'm in here. I saw everything happening in here. I know exactly when I made the decision, right? Turns out in practice for us, and even for these minimally cognitive agents, it's not so simple. Okay, last one. Let's have a look at the figure in the bottom left. Same thing. We're going to analyze just this one evolved CTRNN. The horizontal axis, again, is the initial horizontal position of the pair of objects relative to the robot. So negative values or points to the left in this figure correspond to dropped object pairs that fell initially to the left of the robot. Points to the right, object pairs that were dropped to the right of the robot. Now the vertical axis is going to represent, for the dropped pair of objects, what was the relative aperture width. So a relative aperture width of 0 means the aperture width was equal to the width of the robot. It was just, or maybe just passable if the robot is infinitely performant or capable. But otherwise, points that are in the upper half correspond to passable apertures, and points in the lower half are impassable apertures. If you now think about any individual pixel in this image here, that pixel corresponds to one dropped object pair at a particular horizontal position with a particular aperture width. They then colored the pixel either white, gray, or black. White is the robot did the right thing in that situation. Black is it did the wrong thing. It went for it when it should have run away, or it ran away when it should have gone for it. And gray is it did something in between, which usually means it hit one of the objects, right? You should either run away or get between the pair of objects. You should never be hit by the objects. If this was an optimal robot, this entire figure would be white, right? If it was the worst possible robot, the entire figure would be all black. It's mostly white, so it's mostly doing the right thing. When it's doing the wrong thing, what situations is it doing the wrong thing in?
When the relative width is near 0.
When the relative width is near 0, it's often doing the wrong thing. So you'll see this smudge of black just above 0, which corresponds to the fearful behavior, right? It's running away when it could have actually got between the gap if it did the right thing. Where else is it going wrong?
Around a width of 2, it looks like it's...
Around a width of 2, right? So this is a hugely passable gap, and it's doing the wrong thing. So there's this whole area where something is amiss. Where else? Exactly. So there is this black line here, which corresponds to object pairs that are right above the robot. And it does the wrong thing. So, yes?
I just have a question about the gray.
Sure.
When we say it's doing the, excuse me, when we say it's doing like the wrong thing, do we mean that it's not like passing through the direct center?
Yeah, exactly. It's whatever it's doing, it got hit by one or both of the blocks, right? Which is never the right thing to do, regardless of whether the gap is passable or not.
So would we classify like passing through but not passing through right at the center of mass as like white or gray?
That would be white, right? So if you go between the blocks and you don't get hit, even if you're not directly in the center, that for our purposes, that would be a white pixel. Okay, so the gray is hard to explain, but the black spike that you see in the center here, there is a way to figure this out. And that's by going back to this figure here. As I mentioned, during evolution, every CTRNN is evaluated num trials times. And you can see all num trials here. I don't know if this is 20 or 25, whatever it is. And it's showing exactly where the objects were dropped during evolution. So why the black spike in the bottom left figure?
During evolution, there was never one dropped. Right?
It never saw an object pair being dropped directly above itself, even though during behavior, it gets directly below the objects. It's seen that situation, but just never when the blocks were all the way at the top of the screen, right? So this is a reminder, and we'll see multiple reminders throughout the course, that we need to be very careful with the AI that we train and deploy into the world, because the world is a complicated place, and there are going to be situations that occur with our machines that they have never seen before. And at the moment, at least, no one in evolutionary robotics or any other branch of robotics or AI can guarantee that the machine will do the right thing in an unseen circumstance. It is an open problem in AI and clearly has very practical import. Yeah? Okay. Again, one of the reasons why it's fun to work with minimally cognitive agents is we can see some of these things easier than you could in an autonomous car or a more complex machine. Okay, let's look at the second of the 4 tasks. We're doing the minimal cognition Olympics today, so on to the next event. In this case, we're going to evolve an agent to discriminate between self and non-self. We've actually already encountered a machine that tried to do this and actually did a pretty good job at it. Who was it? BabyBot, right? Remember BabyBot that would move its arm and push on the fruit, and it realized there was this moving blob in its field of view, and it said, that moving blob is self. Because whenever I send commands to my motors, I see that blob show up. Okay, so we're going to see the same behavior here, but clearly in a much simpler agent. This agent is also at the bottom of the screen, but it's immobile. It cannot move back and forth along the bottom of the screen. It has an arm and a hand, which is the little circle, and it can rotate that arm in front of its field of view. And as you can see in the little cartoon here, that hand can occlude its field of view. It can block what it's seeing. So at this time instant, you'll notice that this beam is reporting a shortened length, and this beam over here is also reporting a shortened length. How does the robot know that the thing that is shortening this beam is self, and the thing that is shortening this beam is non-self? Seems obvious to us, not so obvious to the robot.
When you send a message to the arm, if the object coming in doesn't agree with what you're sending the message to, it's got to be the other object.
Possibly. So if I send a command, so if the robot sends a command to rotate its arm, and the length of that beam changes when it sends that command, that's a little piece of evidence in favor of the fact that whatever is blocking that beam is self. But in this experiment, as you see here, the objects that are going to be dropped, and we're only going to drop single objects in this case, they are falling. They are also moving. So the length of this beam is also changing at the same time as the length of the beam, the length of this beam is changing at the same time that the robot is rotating its arm. So it makes things a little bit trickier for the robot here. Question?
The length of the robot arm is fixed, isn't it?
The length of the arm is fixed, yes.
Could you use that as a reference point?
Possibly, right? So there are clearly some hints here that the evolving CTRNNs could pick up. And that's one of them, which is the one that's obvious to us. But there may be other things here that are less obvious to pick up on from the point of view of the robot.
Is the robot trying to block the object with its arm?
We didn't talk about what the robot is trying to do yet. Well, it's trying to do self and non-self discrimination. But it actually has to do that in order to solve the real problem, which is when the object gets close enough to the robot, which is represented by the dashed semicircle here, when it gets within that distance of the robot, it should reach out and quote unquote catch the object. All it has to do is put its little hand where the object is. You can think of it as catching the object or pointing at the object, right? In order to do that, it has to solve the self-non-self discrimination task, right? It's moving its arm, and the length of the beams are changing. Where is self? Where is non-self? I have to figure out where self is, and then everything else is non-self, and then point at that thing. That's what it's trying to do. How does it evolve the ability to do so? Well, again, we're going to drop num trials objects above each CTRN. We're going to evaluate the same CTRN num trials times. We're going to compute its performance in each of those trials. And we're going to compute its performance using the following equation, which has a typo in it in the paper. This should be max and min. As you can see, P sub I is a function of theta sub I, and theta sub I is the angle between the arm and the direction of the object when the object gets to this dashed semicircle. So let's start with theta instead of P. Question? Sure.
Opaqueness of the hand have any relevance since it doesn't, light source sensors go through it?
The opaqueness of the hand does matter. If it wasn't opaque, then we would assume maybe this beam goes through the hand. It doesn't. The hand breaks the beam, right? Okay, let's start with theta. If you're the robot and you're trying to catch the object, what do you want theta to be? What are you trying to get theta to be? Zero, right? You want the angle between your arm and the direction of the object to be zero. So we're constructing a performance measure which is trying to minimize the absolute value of theta. Again, I think they did this in an overly complicated way. You could probably write a simpler version of this. Basically, just get theta to zero in all of the num trials cases. Yeah? Okay, so off we go. We evolve our CTRNs. We get back the CTRN at the end of the evolutionary algorithm that has the highest value of this. And we then replay that evolved CTRN in lots of different situations. The horizontal axis here is we're going to drop a whole bunch of objects, and they're going to hit that dashed semicircle at minus pi over 8 radians or plus pi over 8 radians, right? They're either going to hit near the robot to its front left or its front right. The vertical axis represents the angle of the arm when that happens. How well does this evolved CTRN do? Yes?
It does pretty well with a decent margin of error. You can tell because it barely lines up linearly with like the angles, but there's obviously some room for improvement, and toward the end it has, and the middle it has some issues.
Excellent observation, right? So again, we want the angle on the vertical axis to be the same as the angle on the horizontal axis, regardless of what those angles are. So we want this to line up along y equals x, right? And we can see that generally speaking, as you said, the robot does that. For those of you that haven't seen these vertical lines with the horizontal line caps to them, these are error bars. So they actually introduced a little bit of noise every time they did this. So they actually dropped the objects a whole bunch of times, and they noisified the sensors, meaning that the 7 numbers that are coming back, that are coming into the CTRN, they add a little bit of random noise to them, which kind of blurs the robot's vision, making things even harder on the robot. But it's a good thing to add because in reality, a robot's sensors are not perfect. They also have noise on them. So even if the robot encounters exactly the same situation, which would be any vertical slice through this figure, even if it encounters exactly the same situation multiple times, because its vision is blurry, it's doing slightly different things in that same situation. So we put an error bar. So the vertical black lines say this is kind of what the robot's arm angle was. It's within this vertical range in those conditions.
Do you think that if they had done that in the last experiment, it would have maybe helped to not have that bar where it was exactly?
That's a great point, right? So in one sense, noise is bad for the robot because it means it can't perfectly see the world, but it also means that it can't specialize too much, right? It has to sort of figure out general strategies. So noise, as you mentioned, can also be helpful. And yes, maybe it would have helped the previous robot. That could be something you could explore in a final project. Be a great idea. Okay, as you mentioned also, if you look at the far left and the far right of the lower left panel, the robot does particularly poorly in those cases. It's not really obvious from the paper about why that's the case, but again, not surprisingly, the robot does well in certain situations, but there's a subset of situations, which in this case are far left and far right, where it doesn't do very well. Okay, so again, this panel is showing us, on average, the performance of the robot. What does this evolved CTRNN actually cause the robot to do? And that's shown in the left panel here. Of all the figures you're going to see this morning, this is the one that takes the most to wrap your mind around. I also have to wrap my mind around it every year, so correct me if I get this wrong. You'll notice that we have squiggly lines, and each line has a grayscale value. Okay, so each squiggly line corresponds to one dropped object, and the motion of the line is showing you the motion of the angle of the robot's arm. And you'll notice that at the end, all of these lines get to an angle of 0, or a vertical position of 0, which means that the angle of the arm is equal to the angle of where the object hit. So far, so good? Okay. You'll notice that a whole bunch of these lines emanate from the far left, which corresponds to, let's see here, let me make sure I get this right. It's the initial angular position of the arm. So when they drop the object, they're going to drop a bunch of objects, and in half the cases, they take the robot's arm and rotate it initially to be to the left, and the robot starts moving from that initial left position. And in the other half of the cases, they crank the robot's arm so that it's angled to the right, and then the robot starts moving its arm. So the initial positions here correspond to the angle of the arm. I'm sorry, I misspoke. Okay, so down here, when we're at an angle of 0, that means that the arm is pointing straight up. The color of the line, the amount of white or black here, corresponds to the initial angle that they drop the object. In all of these cases, they're going to drop the object at different horizontal positions at the top of the screen, but in all cases, the objects are going to fall diagonally, and they're all going to hit directly above the robot. So they're all actually heading to the same position. The robot doesn't initially know that. So they're all falling from different horizontal positions towards the center of the robot. And in all cases, this robot ends up pointing its arm directly straight up. So the horizontal position of the lines corresponds to the angle of the arm. Yeah? So the geometry of the curve is the angle of the arm, and the color of the curve corresponds to where the object came from. So far, so good? Okay, let's look at a few individual trajectories to get the idea of this. You'll notice that here's one trajectory, the one on top here, that starts very lightly colored over at the left. What does that mean? What's happening in that, for that one line, that one trajectory, what's happening? Tell me about the arm and tell me about the object. Or the initial position of the arm, the initial position of the object.
They're starting at opposite sides.
They're starting at opposite, right? The arm is off to the left because the trajectory is off to the left, but it's lightly colored, which means the object started over to the right. Yeah. There's another lightly colored trajectory over here, which corresponds to what? What's happening in that case? The arm is at the right because the trajectory starts over to the right, and it's lightly colored, meaning the object started from over there. You'll notice in this band of trajectories that are all together, this is all where the arm started to the left. In all cases, the robot extended its arm further to the left and then started to bring its arm back towards the center. And then all of the lines start to diversify. The darker colored trajectories head back over to the left, which means the object is to the left because of the darker colored trajectories. And the arm starts to go back towards the left. And we get a whole bunch of black trajectories over on the left and a whole bunch of lightly colored trajectories over on the right. What does that tell you about what the robot is doing in general for these different dropped objects? It's keeping its arm on the same side of the object, and it's not keeping its arm still. It's waving its arm back and forth in the direction that the object is coming. Seems like kind of an odd thing to do, right? You would imagine if you're trying to see this object and figure out where it's going to hit, best thing to do, move your arm out of the way. At the beginning, no matter what's happening, just move out of the way, watch it, figure out where it's going to hit, and bring your arm there, right? At least to me, that seems more obvious than deliberately obfuscating your vision, right? It's waving its hand back and forth in front of the object.
You said all the objects were aimed at the center, right?
They're all falling towards, they're all going to hit just above the robot.
So why do we have the white gray markers in that center portion right there where your mouse is?
So remember that the color of the line is the initial angle of the object. Obviously, the angle of the object is changing as it's falling because it's going to hit front. That's not the color of the line. Kind of interesting, huh? What does it do? In most cases, it's sort of waving its hand in front and then just at the end brings the hand to where it's supposed to be at the right time. What about what's going on in here? Medium gray.
Kind of confused what to do.
Maybe it's confused, right? We're using Bratenberg language here. Clearly the robot's confused. It's sure. Who knows? These are objects that started falling from directly above, right? Medium gray. And if you follow those lines back up, the arm is somewhere else, right? It's doing something and then it sees the object falling and is waving it in front of its face. Seems like kind of an odd thing to do, but clearly it works for the robot. Just yet another example that thinking about thinking is misleading.
Okay, I think the robot continuously wants to know where the object location is.
It absolutely wants to know where the object is and where it's headed.
And that is why it keeps on vibrating around that point. Because the robot, in a sense, like a child needs to go where at every point where the object.
True, but the robot still could move its arm out of the way and see with its broken beams, the beams that are being broken by the falling objects, it can quote unquote see exactly where the object is.
So like in our case, like we see two eyes and we act on the arm. But like in the robot case, like the arm is actually an eye.
The arm is not an eye.
And like acting like a one, it seems to be.
I see. It's sort of turning, the arm can selectively turn off some of the beams. That's true, yeah. Hard to say, right? Okay. Okay, let's look at the third of the four minimal cognition events. In this case, we're going to go back to a robot that is moving left and right towards the bottom of the screen. We have objects that are falling, and they can fall, any one object falls in a straight line, but they can fall at different angles. They can fall straight towards the robot, they can fall at an angle. The robot has dashed lines in this case for its eyes, which is a visual cue to remind us of what this robot, actually, it's going to remind us of a disability that this robot has, which is the moment the robot starts moving, the sensors turn off. So as long as it stays immobile, it's receiving 7 numbers from the 7 beams. But the moment it starts moving, and even if it stops again, it's blind for the remainder of the trial, and it's only receiving 7 zeros from its sensors at each time step until the end of the evaluation. Why do that? Because obviously it's going to force the robot to remember something. What is it trying to remember? It has to remember when and where the object is going to hit. So in this cartoon here, let's imagine at this time instant, the robot has not yet moved, so it can see. So it's getting back these, well, maybe it's 9, doesn't really matter. It's getting back these numbers to its sensors. At this single instant, it cannot tell whether the object is falling straight down or falling to the right. It's going to have to sit immobile and watch for multiple time instants to see the deltas, the changes in the length of these beams, which provides evidence about the angle, the velocity at which the object is falling. And it has to remember that somehow when it starts moving. How does a CTRNN or how does any neural network remember? What do you need to have for that to happen?
Hidden layers inside the
Hidden layers and
memory block.
not a memory block.
Self loops.
Self loops are recurrent connections, right? It needs to be, the recurrent connections feed back into the network values from the previous time step. A neural network that has no recurrent connections cannot remember anything from the previous time instant. You can go back and have a look at the neural networks lecture with the simple and or neural networks. They can't remember anything. Okay, so somewhere in this CTRNN is recurrent connections, and it's got to remember how to do so. We're going to, again, evaluate every CTRNN multiple times during evolution. What are we trying to do? In this case, we're trying to minimize the absolute value of d sub I, which is a reminder that we're trying to get d sub I to be as close to 0 as possible, which is the final horizontal distance between the robot and the object when the object hits the ground. So the robot needs to be there when the object hits the ground. So not only does it need to figure out and then remember where the object is heading and when it's going to hit the ground, but it's got to use that information to set its own movement pattern to be there when that happens. Okay. Surprise, surprise, it involves a CTRNN that does this, but it doesn't do it perfectly. So again, the figure in the lower left, you would imagine that optimal behavior means that every final object position, the horizontal axis, so where on the ground horizontally does the object hit, you would expect the exact same horizontal position, final horizontal position for the agent, which is on the vertical axis. The robot should have the same horizontal position as the object when the object hits. They should all fall along the line y equals x. Doesn't happen. Where's the robot having issues here? At the extremes and...
At the middle. 0.
Okay, so hard to explain why it's having problems in the middle, but again, by now you'd imagine maybe it doesn't have a lot of experience with objects right at the middle. It's also, again, having problems at the extreme. The picture in the upper left should give you a hint about why the CTRNN has a hard time with objects that hit far to the left and far to the right of the center of the screen. Why is that difficult?
Because it's angle of view, field of view.
Absolutely, right? So if you think of this fan going up from the robot, objects that fall far to the right or left probably are starting around there, which means the robot only sees those objects for a very short period of time before the object passes out of the robot's field of view. The robot wants to see more of the object, so it starts moving towards the object and it goes blind. So it can't get any more information, right? It's got a very short time to figure out what this object is, how fast it's moving, and at what angle. Okay. Same thing, an evolved CTRNN. We're going to drop a whole bunch of objects at different initial horizontal positions at the top of the screen. And they're all going to fall straight down in this case. You can see the vertical lines, which on the vertical axis here are representing the vertical height of the object. And the horizontal position along the bottom of the screen. Where's the sorry, this should not be horizontal position, horizontal distance. The distance between the robot and the object at the bottom of the screen when the object gets there. They all are near 0, which means mostly the robot is doing the right thing, right? It's getting there. Again, in this case, black lines are showing correct behavior. They're all close to 0. The robot's doing the right thing in this case. And the gray lines, the robot's not doing as well. The gray lines are further from 0 at the end. The robot didn't quite get there in those cases. Why? It's the difference between the black and the gray lines. What's the difference between the black and the gray behavior?
Looks like the gray lines are when it's really close to the robot initially or far away.
So exactly. So there are these ones that are very close. They're directly above the robot almost, and it does the wrong thing, which is probably because it didn't see those situations during evolution. And as we saw in the previous figure, it has a hard time with objects that start falling straight down, far left and far right. The robot only sees those for a very short period of time. When does the robot decide? When does the robot know where and when the object is going to hit and start moving based on that information? Okay, you're all getting it at this point, right? It's a trick question. Who knows? Hard to say. Let's have a look at the same C tier and N. The only thing we're going to change now is instead of dropping objects straight down, let's skip to this one. This one's a little more interesting. Instead of dropping objects straight down, we're going to drop objects at angles. So we're going to take the same C tier and N, drop a whole bunch of objects at the top of the screen, but they're all going to fall down and to the right. What does the robot do in this case? It acts differently as it did in this case. How? What is the robot doing differently? How does the robot handle obliquely falling objects compared to objects that are falling straight down? If you stare at this picture in the top left for a while, you should be able to sort of figure out how the robot is moving. We know how the objects are falling. They're all falling at the same velocity, at the same oblique angle, regardless of where they drop them from the top of the screen. What is the robot doing?
It moves to the left, almost like it's moving towards where the object started, but horizontally, but where it won't hit when it gets to the bottom.
Okay. What else is different? Is it heading straight for the object? It moves back and forth more, right? Which is kind of strange. Objects that fall straight down, it heads straight for the object. Objects that are moving obliquely, it's jinking as it moves. Why? Who knows, right? Remember, it's blind, so it's not scanning the object as it moves, like we saw in some of the previous cases. Same thing if we drop a whole bunch of objects from the center of the top of the screen, but they all fall at different angles. The robot, again, is jinking as it moves, and each of those trajectories is slightly different depending on the object. Kind of strange, but generally speaking, at the end, the robot is in the general vicinity of the object when it gets there. It's kind of an interesting detail. All right, let's move on to the fourth and final event. This is my favorite one. We may not have enough time to finish this, so we'll just introduce this. We're now going to look at selective attention, which our society as a whole is increasingly struggling with. At the same time, you are hopefully trying to listen to lecture and pay attention to this. You may have felt your phone vibrate in your back pocket, or remember that you missed a dentist appointment this morning, or there may be an alert going off on some other device that I can't hear. The devices in our world are increasingly grabbing our attention. We are increasingly challenged to select where we allocate our attention, right? It is a difficult thing to do, what to decide to focus your attention on. Always difficult to do, becoming increasingly difficult with our increasingly instrumented world. So we're going to evolve a robot that not only attends or pays attention to the object, but has to selectively switch its attention from one of the falling objects to the other in its environment. So we're going to go back to dropping pairs of objects in the robot's environment. They are both going to fall towards the bottom of the screen. But as you can see with the dotted black lines here, these objects are going to fall at different velocities in different directions. And as you can imagine, we're going to try and evolve a robot that collects both objects. Whichever object hits first, the robot's there. When the next object hits, wherever it hits, the robot is there. That's selective attention. We are again going to select for performance, and they've switched this around here, which is not an elegant way of doing this. The overall performance of a single CTRNN is negative p sub I, or the average of all the p sub i's. And we're setting p sub I to be proportional to the distances. So the easiest way is to do a little bit of arithmetic in your head. We're selecting, as usual, for all of the d's to be near 0. But we have two sets of d's in this case, d sub I1 and d sub I2. d sub I1 is the horizontal distance between the robot and object 1, the first object, when that object gets to the ground during the ith trial. And d sub I2 is the horizontal distance between the robot and the second object when the second object gets to the bottom of the screen. We're trying to minimize both, right? Be there in both cases, regardless of when and where those events occur. Okay. I had a student who took this class a few years ago who tackled this in a final project, and they implemented this in PyroSim, and here's the result. Hopefully by watching this video, you get an idea of why this task is so difficult.
So it doesn't go blind.
It does not go blind in this case. It can move and see at the same time. There are many things going on in this video. What are some of the things that are making this task so difficult on the CTRNN?
The variable speed.
Yeah, determining which one's like moving faster, which one's going to land first.
Determining which is moving faster. So assuming it computes the velocity of these objects and knows which one is moving faster, does it go after that object? Should it always go after the faster moving object? Not necessarily. Why?
Because they're not starting at the same spot.
They're not starting. Some of the objects, one object starts closer to the robot than the other. So the most difficult situation for this robot is the object that is initially further away is moving faster, right? So it's a pretty tricky thing to do. What else makes this task difficult for the robot? How do you know that it has memory inside the CTRNN?
Because when one goes out of its sensor, it knows what side of the screen it's on.
It knows, right? We've got to put mental quotations around all these things. It knows where the other object is, and most importantly, it knows where it's heading, right? You'll notice that in some cases here, when an object passes out of its field of view, it luckily starts moving back towards that object, but does it at different velocities. You're watching exactly the same CTRNN played back in multiple situations, right? So a lot of things going on here, right? You also need to keep a mental to-do list and remember which things are more urgent, which things have been on your mental to-do list for longer than others. Very, very difficult task even for humans to solve. Okay. So as mentioned, in this case, the robot has to solve in order to solve this task, there are certain sub-problems that the robot needs to deal with. Two problems. The first one is the passing objects problem. The object that is further away, in some cases, the object that's further away is moving faster. So it can't just pay attention to the closer object and go after that. At some point, one object is going to pass another, and it's going to have to then go after the new leading object. if you think about it, maybe the passing objects problem is not that much of a problem. Watch both, and watch the passing event itself, and just wait till the objects have passed one another and chase the leader. For most of the situations in this task, it's not that simple. Why not? Why not simply just watch both objects pass one another, if they do? Could be too late. How does it know? It's already paying attention to one. It can't see the other. Not so easy to do. And as we already mentioned, there is at the same time this additional problem, the object permanence problem. The robot can't permanently watch both objects all the time, right? There are lots of things going out there in the world right now that you can't see that are going to positively impact you in the future. And you want to, at least for the ones you know something about, keep them in the back of your mind and remember and select your attention back to them when necessary. Okay, I think we'll finish this on Thursday. You have a quiz due tonight. You're tackling assignments 5, 9, or 10. See you on Thursday.